Sorry for the delay. My name is Sharon Lapiner. I work with Avishai Dekel at the Hebrew University and the rest of the group. I'm going to talk about compaction to a blue nugget and the connection to black hole growth. So let me start by just showing you the sequence of events. This is the Villa simulation by Daniel Severino. It's a very high resolution simulation. We look at here in the 34 galaxies and see the general behavior of this sequence of events. So we start by, where is it? Yes. We start with a very disturbed configuration of the gas. The gas is in the top row. Okay.
Because I'm not picking up your slides, so I can see it after.
Okay. Okay. So we see a disturbed configuration of the gas. There's a lot of gas coming into the galaxy, and the next snapshot, we see here compaction to a very dense core of gas. This is the peak of compaction, which is what we find as the blue nugget. If we compare to observation, this is what we expect to see as the blue nuggets observed by Barrow and others. At a later stage, we find a post-compaction disk forming around this nugget. This is something that Avishai, I think, will talk about. And at much later stage, this is the redshift 1.5, around 1.5, we see a nice ring coming in, and the center is depleted from gas. The star formation rate is occurring at the outskirts and less at the center. This is close to where we would see the red nugget seen in observation. And in the stars, we see a similar configuration. We find the gas is funneling at the blue nugget. Here we see that a lot of the inner 1 kpc stars are forming during this stage. And later on, if we look just at the center, it doesn't change much, meaning that there is a quenching in the center. So this is just a cartoon looking within 1 kpc, the mass versus the time. This is the gas. We start from a diffuse configuration, then compaction of the gas by an order of magnitude, and depletion of the gas from the center and quenching in the center. In the star formation rate, you see about the same thing. It's designed to be about the same thing. And in the stars, we see post-compaction, post the peak of the compaction, we see quenching in the center. The stars are not growing. We find these are all the galaxies in the simulation, and looking at the mass, or specifically here the viral mass versus the redshift, we see that all of these, each point will indicate the peak of compaction. So we find that they're all occurring around the same mass with relatively small scatter. And the same for the stellar mass, a bit more scatter in the stellar mass. This is occurring, it's a critical mass for the blue nugget at all redshifts, at least for this sample of galaxies. At all redshifts, we see something like a stellar mass of 10 to the 10 and a viral mass of 10 to the 11.5. Maybe higher. So below this mass, the supernova feedback is suppressing the occurrence of this compaction by just every time enough gas is coming in, it's blown out very fast since the potential well is too shallow. And once you get to this threshold, the compaction succeeds to occur by funneling much more gas. And above it, the hot CGM will prevent the accretion of the gas. Oh. What happened? Oh, no, that's fine. Sorry. Sorry. So, what I wanted to, we see a lot of transition during this compaction phase, and what I wanted to focus on was the compaction and the connection to the black hole growth. To do this, we analyze the New Horizons simulation with working with Johan Dubois. And I'll start by showing just the set simulation. It's a similar simulation. It was done in 2 flavors, with and without supernova feedback. And we see here that, okay, so this is the mass of the black hole. This is the time. If we look at the red line, this is with no supernova feedback. The black line with supernova feedback. We find that if we add this supernova feedback, the black hole growth is suppressed in this until some critical mass. And once you reach this point, there's a rapid growth. If we look at the no supernova feedback, the growth is instantaneous or very early. So we find in this case, there's a merger occurring just before this, this growth of the black hole. And okay, so this is the effective radius versus the mass of the galaxy. And this is the merger. And once you see this, after this merger, you get a decrease. The galaxies becoming compact, indicating the compaction here. So this is indication of the compaction. So below the critical mass, strong supernova feedback suppress the black hole growth. Compaction overcomes this, overcome the supernova feedback once the potential well is built. And at a later stage, the AGN may help the quenching. So this is the New Horizons simulations. Here I'm using just 2 galaxies as an example. You'll see the blue line is the gas within 1 kpc. It's focused on the blue line, and the black line, the black thick line, the black line is the black hole mass times 10 to the 4. And we see a compaction followed by black hole growth. In this case, again, this is just the evolution. We see the growth of the gas within 1 kpc by an order of magnitude. And then the black hole growth is the mass of the black hole is growing following this compaction event. The gas funneled to the center by this compaction is helping the black hole to decay to the center, which I'll mention in a minute. And the potential well will hold it inside. So this is the radius of the black hole with respect to the center of the galaxy. And what we see here is that before this compaction event, the black hole was wandering around 1 kpc. It's not pinned to the center. It was wandering, and once you get enough gas, the black hole is dragged by this gas and the growth of the potential well due to this compaction, and it's decaying to the center of the galaxy. And we find this in all the galaxies. In some cases, we see some of the black holes are migrating again if the black hole, if the mass of the galaxy is not high enough, but it will come back to the center once the potential well is deep enough. So this is black hole mass versus stellar mass. And you can see again suppression of the black hole mass by supernova feedback before this magic scale of something like 10 to the 10. And this is followed by the compaction, which will drive the black hole to rise to something like the known relation at low redshifts. This is a robust in other simulations. We see it in Eagle, in Illustrious, in Fire. In all of them, there's suppressed black hole growth followed by a increase after some mass, which is a critical mass, which will probably depend on the feedback in each simulation, the value itself. So this is observation, Kachevsky. We're looking at the star formation rate. It's growing this way, and a measure of compactness, the sigma effective. And we find they find that in a diffuse phase, the AGN, the color is the AGN fraction within each bin. In the diffuse phase, there's less AGNs, and once you get to this region of compact and star forming, there's high probability for AGN activity, which is the region of the blue nugget. So compaction triggers the black hole growth, which means that you'll get an AGN activity, and eventually, probably, it will help the quenching. This is Forster-Schreiber results. Seeing, again, it's a fraction of AGN versus the stellar mass. And here I'm showing this is the same line taken from these results. And in order to get something similar to convert from the simulation to the observations, I'm calculating from the accretion of the black hole, the expected luminosity, and then each line will be the threshold for some luminosity of a black hole. And we see here, this is the accretion rate versus the stellar mass for something like what was the threshold in this paper. It was about this value, this green line. And if I plot now the fraction of AGNs by each of these lines, and if you look at the green line to compare, we see a similar result. The exact value where you see this transition of the mass is not, it's not the crucial point, but what we want to show is that it's the same effect, the same transition. So I'll just skip through. Below, this is my early conclusion. Below the critical mass, the supernova feedback is more effective. It can evacuate the gas. Black hole formation is suppressed. Blue nugget formation is also suppressed, which is doesn't help the black hole to grow. But once you get to the critical mass, the compaction is overcoming the supernova feedback. Compression of the gas activates the rapid black hole growth. It also drags it to the center in case it's not in the center, which is another factor. And above the critical mass, you get the hot CGM phase. The supernova winds are bound, the gas falls back, and the black hole can continue to grow by the recycling. And did I forget something? Okay. So the compaction to a blue nugget is a dramatic phase. We see many properties of the galaxies going through transition during this phase. The last major compaction to a blue nugget occurred at a typical stellar or virial mass when the supernova feedback becomes less effective. Below the critical mass, supernova feedback will suppress the black hole growth, and above it, wet compaction is triggered and the black hole will grow. Yes, that's it.
Questions?
This is just a comment for theorists and simulators. So on the observational side, there are a lot of papers where people will just have a galaxy sample and they'll go and identify AGN, and then they'll make plots of things like fraction of AGN as a function of galaxy properties. Those are really strongly impacted by AGN observational selection biases, and the most severe one is that more massive galaxies have more massive black holes, and the Eddington ratio distribution is very broad. So what that means is to a given flux limit of a survey, you will artificially identify more AGN in massive galaxies simply because you can see further down the luminosity Eddington ratio distribution function than for lower mass black holes. So certain observational papers take this into account and certain ones don't. So you just want to be very, very careful that you're comparing to ones that don't just say, here's an observed AGN fraction as a function of stellar mass, because it'll always be too steep compared to what the reality is. So the way that you correct this is, instead of just saying, here's a fraction as a function of stellar mass or something, you can measure the actual Eddington ratio distribution function where you've divided by stellar mass, look at that as a function of stellar mass, and it's accounted for. So there's ways to do this, but this, I feel like this is maybe not well understood amongst observers, that you need to be careful about which papers you're comparing to. Just a comment.
Okay, thanks, nice talk. So I'm a bit confused about one thing. You argued that supernova feedback is the main driver, but I thought from one of your plots you actually showed that it's really where the black hole is. So before essentially the black hole settles in the center, it doesn't grow very much, which is kind of expected, and then because of, let's say, the compaction, the central deepening of potential well, the black hole in your simulation settles in the center, and now it can grow grass, grow gas. So what had this to do with feedback?
So if we had, you've seen the simulation that had with supernova feedback and without supernova feedback. Once you have okay, let's say you don't have a very strong or at all any supernova feedback, the potential well will grow very early, right? Then it means that the black hole will decay to the center very early. This is what is driving the black hole to the center, this and being just dragged by the gas into the center, which means that the fact that the black hole is migrating is due to this fact, due to the fact that supernova is suppressing the growth.
Okay, so what you're saying essentially is supernova feedback is just a mitigator that essentially is important for the setting the potential well, if I understand it correctly. Yeah?
Yeah.
Okay, thanks.
So this is very interesting and a nice analysis of the simulation. It's more common than a question. So people have been showing that supernova feedback is able to regulate black hole growth in low mass galaxies, including myself. And I think we were thinking only about looking at the supernova feedback effect. But I have a paper in preparation where I'm also looking at the AGN feedback, because in those low mass galaxies at redshift 0, we do see AGN in dwarf galaxies. So they must, even if the accretion rate is not as high as you would expect in massive galaxies, I think they can still, we see them, so they must have an effect on the galaxy. So I think the picture that, supernova feedback, definitely I think it's the most important effect, but I think the picture may be slightly more complicated if you look carefully at the AGN feedback and supernova feedback. But very
Yeah,
nice
so
work.
I do have maybe one or two examples from the small sample I have where I see a small compaction event occurring very early on, and there is some black hole growth. This will be probably an AGN for short term. So I think it could explain this.
Okay, I think we have to move on. Or is it this a quick question while he sets up? Okay. Then let's thank the speaker again, please.